Hello everyone and welcome to Tutorials. Today we're gonna learn how to perform the binary search algorithm. Given an array of integer nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index. Otherwise, return -1. You must write an algorithm with O log n runtime complexity. So the question prompt essentially asks us to apply the binary search algorithm to the given input array to find the index of the target value within the array. Binary search is a very important search algorithm, and knowing it provides a very strong foundation for future problems, so I cannot stress how important it is. Let's take a look at some examples to better understand what the problem wants us to return. In the first example, we're given the following input array and a target value of 9. Since 9 is contained within the fourth index of the array, we need to return 4. In the second example, we're given the same array as before and a target value of 2. Since 2 is not contained within the array, we need to return -1 as per the question prompt. Now for a minute, let's forget about the time complexity constraint of the problem and talk about what the most basic solution to this problem is. Performing a linear search over the array using a single for loop, we can determine the index of the target value in linear time if it's contained in the array. That is, checking every element of the array one by one and comparing it to the target value. Once we find an equality between the current visited value of the array and the target value, we can immediately return the index. Else, if the target is not found within the array, we will break out of the for loop and return -1. This method has a time complexity of O of n, where n is the length of the array, and a space complexity of O of 1, since we do not need an auxiliary extra space. However, as given in the question, we're dealing with an already sorted array. In questions like this, where the prompt explicitly states that we're given a sorted array, there usually is a clever way to utilize the sorted property to reduce the time or space complexity. And that is why the question also explicitly wants us to find an algorithm that is logarithmic in time. Now let's talk about how the binary search algorithm works, which is going to enable us to solve this question in O of log n runtime complexity. So the problem with the linear search algorithm is that we're considering every element in the array. But since we're given a sorted array, we know that if a value given in the array is less than the target value, we can be sure that all the values to the left of the current value are guaranteed to be less than the target value, so we can eliminate them altogether without visiting these elements. The same applies to a visited value that is greater than the target value. In that case, we can eliminate the elements to the right of that value without checking them individually, because they're guaranteed to be greater than or equal to the current visited element, since the input array is already sorted in non-decreasing order. This is actually the most critical aspect of the binary search algorithm, so I cannot stress it enough. We will start by considering the middle element, and if it's greater than the target, we will eliminate the right half of the array and only consider the left half in the next step, and it's going to be the opposite if the middle element is less than the target. Then we will consider the middle element of the non-eliminated half and apply the same logic on and on until we find the target, or conclude that the target does not exist within the array. This way, we will reduce the space searched by half at each step of the algorithm, which will lead to a logarithmic time complexity. In order to calculate the index of the middle element, we will use 2 pointers initialized to the 2 extremes of the array, which will also mark the beginning and end of the portion that is still being searched by the algorithm. As soon as we find the target value, we will return its index. If the target value does not exist in the array, the algorithm will run until the left pointer surpasses the right pointer, as left surpassing right means there's no longer any valid interval within the array to search. The verbal explanation might be a bit vague for you right now, so let's see how this algorithm works on an example. Let's say we're given the following input array and a target value of 9, and note that these values represent the indices of the individual elements, which I've included for you to better understand the example. Initially, our left pointer is initialized to the 0th index, and our right pointer is initialized to the 13th index, which are the 2 extremes of the array. This also shows that the whole array is being searched for the target value. We're going to calculate the mid pointer by taking the average of left and right pointers and rounding it down to the nearest integer. So 0 plus 13 divided by 2 is 6.5, and rounding it down to the nearest integer gives us 6. So our mid pointer is now pointing at 5, and since 5 is less than our target value, and the elements to the left of 5 are guaranteed to be less than 5, because we're given a sorted array, we can eliminate this half. In order to eliminate that half, we're going to reassign our left pointer to mid pointer plus 1, which is the 7th index. Now our left pointer points at the 7th index and our right pointer still points at the 13th index. This means that we're searching for this portion of the array for our target value. And since our left pointer is less than or equal to our right pointer, we can continue looking for our target value in the right portion of the array. Let's recalculate our mid pointer. 7 plus 13 is 20, and dividing it by 2 gives us 10. Now our middle value is pointing at this 12, and since 12 is greater than our target value, we can eliminate all the values that are to the right of 12. In order to do that, we need to now update our right pointer and set it to middle index minus 1, which is 9. Now our left pointer points at 7 and our right pointer points at 9. This means that we are looking for the target value in this portion of the array. Now, since our left pointer is less than or equal to our right pointer, we need to update our middle pointer. We're going to do this as we did before. So 7 plus 9 is 16, and we are dividing it by 2, which is 8. So our mid pointer is pointing at the 8th index, so our middle value is 7. Since our target value is greater than 7, we can eliminate all the values to the left of 7. We're going to do this by updating our left pointer to middle pointer plus 1, which is 9. Now our search space is only reduced to a single value, which is the value of 9 at the 9th index. Since our left pointer is less than or equal to the right pointer, we need to recalculate the middle pointer. And 9 plus 9 divided by 2 is 9 as well. So our mid pointer is pointing at 9. Since 9 is equal to our target value, we need to return its index now, which is also 9. Please note that the values that are pointed by these 3 pointers are just indices, not the values themselves. So it's a coincidence for this 9 and this 9 to be equal to each other. The bottom 9 is the value and the top 9 is its index. And in the last step of the algorithm, we've checked if this 9 is equal to our target value, and we've seen that, so we returned this 9. The same result would have been obtained if we had an 8 here and an 8 here. Let's take a look at some other case where we have the value 8 in the 9th index and we're looking for target 9 within the array. Since the array does not contain 9, we need to return -1 in this case. And let's say that we're at this step of the algorithm where the values to the left and right of the 9th index are all eliminated and our search space only contains one element, which is this value of 8 at the 9th index. Now our mid pointer points at the 9th index and our value of 8 is less than our target value, so we need to eliminate all the values to the left of 8, including 8 itself. So we're going to be moving our left pointer one place to the right of our mid pointer, so now our left pointer points at the 10th index. Now as you can see, our left pointer is pointing at the 10th index and our right pointer is pointing at the 9th index. Now since our left pointer surpassed our right pointer, we need to return -1 since we no longer have any valid interval within the array to search. Thus, we can conclude that our target value is not contained within the input array. Now let's talk about the time and space complexity of this algorithm. As aforementioned, the time complexity is logarithmic in n, and the space complexity is O of 1 since we're only using 3 extra pointers, which is a constant amount. Now let's see how we can code this solution. The first thing I'm going to do is initialize our left and right pointers to the 2 extremes of the array. Now we're going to be performing the binary search algorithm while the left pointer is less than or equal to the right pointer. And as I've mentioned before, we're going to calculate the mid pointer by taking the average of left and right pointers and rounding it down to the nearest integer. In Python, this operator will allow us to do so without using the floor function. Now I'm going to access the number at the middle pointer and check if it's equal to the target value. If it is, we're going to return the mid value because we have found our target value within the array and we know its index, which is the mid pointer. Else if the number is less than the target, we're going to eliminate all the numbers that is to the left of num. So we're going to set our left pointer to mid pointer plus 1. And if our num is not equal to the target, and if our num is not less than the target, it must be the case that our num is greater than the target, which is our else case. And in this case, we need to shift our right pointer to the mid pointer minus 1. This portion of our code is the bread and butter of our algorithm because shifting our left and right pointers according to the mid value is going to enable us to reduce our search space. And now if we don't hit this if statement until we break out of this while loop, in which case our left pointer surpasses our right pointer, we can be sure that the target value is not contained within the nums array, in which case we need to return -1. And that's actually it. And let's submit our code. And as you can see, our algorithm is correct and pretty efficient. I hope you found this video helpful. And if you did so, please leave a like and subscribe. I really appreciate your support to the channel a lot. And I'll see you in the next one.